Society. This is chapter 2, Atoms from Chill's Chemistry for Changing Times. Speaking Dr. Tania Cordova Santiago. So, in this chapter, we're going to see what how the concept of the atom was introduced after the Greeks believe in different models say that everything was continuous and not made of particles. So that concept was introduced later after Democritus. So we're going to see that, and then experiments that led to the law of conservation of mass, and the law of definite proportion. This is explained in terms of the atomic theory. We're going to see composition of compounds. How we do some calculations? And we're going to also talk about the mole concept, calculations involving mass and mole. Also, how the elements are organized in the periodic table. Then, what is the difference, atoms and molecules? And finally, something about green chemistry. In this course, we're going to be always making connections with green chemistry. Now, in the beginning, so this is notice even 384 before Christ. So this is very old. So the Greek had the idea that all the matter, the word like four essential elements, which I have here, so fire, water, earth, and air. And so in that matter was something continuous, no particles. And so that was the beginning of the idea. And science was a little bit chemistry. All the chemistry that was done up to say 1700 was about alchemy. And but up to that point, we have like the Enlightenment period of science, and then we had some changes occurring. But before that, uh, it was the idea of Democritus that the matter had to be subdivided in smaller particles because if you look at the sand, that was his idea, uh, you see from afar it looks like it continues, but when you look it up closely, you see grains of sand, so you can think that you can divide that further and further until there's no point you cannot divide it anymore. Same with water. You can visualize some surface of water and then think of a drop in something even smaller than a drop until no longer you can divide that. So that's the Democritus idea. And as I said before, everything was kind of not advancing much in chemistry except for alchemy until the 1700s. And several experiments led Lavoisier to um, propose the law of conservation of mass, which says essentially that if you have a chemical change, the mass is neither created nor destroyed, so stays the same. In the picture here, we have Lavoisier and his wife, which actually was also a scientist. So here's an example of what is the law of conservation of mass. If you have here 100 grams of mercuric oxide, which is a reddish powder, it can be decomposed, giving 92.61 grams of mercury, and that's a liquid with totally different properties. Mercury liquid, and this coming from a solid like a reddish dust, and it also forms 7.39 grams of oxygen gas. So here you see the relationship, but notice that if you add 92.61 and 3.39, it adds to 100. So no matter what's created, we have the same amount of the same mass. With that, we can say propose some calculations. So what happened here? I have a question. When 20 grams of mercuric oxide decomposes, it forms 1.478 grams of oxygen. What mass of mercury forms? So there's a couple of ways to see that. Notice that 20 grams, we have the equation that we have above. 20 grams is one fifth of 100. If you divide 7.39 by 5, you get 1.478. And also, if the law of conservation holds, the mass of mercury that formed plus the mass of oxygen should give you 20. In other words, you can calculate the grams of mercury that formed by subtracting 1.478 from 20, and that gives you 18 something grams. So do the math and you see that. But also, you can, if you did 92.61 over 5, you will get that number again. But the point is that it needs to add to this number. So because that matter is neither destroyed nor created, so it has to add to 20 grams. Now, there is another important law in chemistry, which is the law of definite proportions. And this was by Proust. And is that a given compound, whatever that is, say sodium chloride, is always composed by one molecule of sodium chloride by one sodium and chlorine. And it regardless where it come from, the source, it will be exactly having the same composition, discrete proportions. So here you have copper carbonate from different sources like malachite, this roof here, or this powder. All of that copper carbonate contains exactly the same, and copper carbonate will be, let's write this. So Cu, and then we have CO3. Oh well, my number is not the greatest. Okay, CO3. Meaning that regardless where that compound comes from, the source, its composition is the same. Okay, so that's the law of definite proportion. Here's an example by an experiment by Berzelius. And here, if you mix 100 gram of lead with 1.55, 10 gram of lead with 1.55 gram of sulfur, you get 11.55 grams of lead sulfide. Notice the law of conservation of mass, because if you add 10 and 1.55, you get 11.55. So the law of conservation of mass. But also, if you now add 10 grams of lead and 3 of sulfur, you still form the same amount of lead sulfide, but you have some sulfur left over. So it's very specific proportion. It needs to be 10 with 1.55 to actually consume all of these two regions completely. And now, if you have 18 gram of lead, so much more, with the same initial amount of 1.55, you still form the same amount of 11.55 gram, but now you have leftover of lead, meaning that this two mix in this specific proportion. If you have a bit more of lead, but exactly that amount of sulfur, like in the third line, you will have the same amount of lead sulfide. And again, keeping that specific proportion, if you had 100 gram of lead and you use 3 grams of sulfur, you will form the exact same amount of lead sulfide and you have sulfur left over. So definite proportion, always in those same specific amount or relationship. Now, it was later John Dalton proposed the atomic theory of matter. We have said before, like the grain of sand, if you guys remember, thinking in the matter, dividing in a smaller particle until it can no longer be divided. So John Dalton proposed the atom and applied that to the law of multiple proportions. And if you think of the particle, nitrogen oxide, and here you can do, notice here, nitrogen oxide has one atom of oxygen. Here you see oxygens are the red dots and nitrogen is the blue. So you have two dinitrogen oxide, meaning we'll have two nitrogens, one oxygen. Always in that proportion. and that's the amount, the ratio of the masses. If you have nitrogen monoxide, it's 1 to 1. But this element, so this is the ratio of the masses. So, but again, very specific. The dinitrogen oxide will always be formed this way, in this ratio. And same with nitrogen monoxide and nitrogen dioxide. So it was demonstrated, and that ratio was obtained, say, by dividing the mass by the smallest. The ratio of the masses that combined with oxygen is divided by the smallest amount. So 0.475 or 0.4375. This. All right. Now let's continue with John Dalton and the theory, the atomic theory of matter. So these are the smallest particles that you can get that have actually the properties of any element. So that any all of the atoms or of a given element would be exactly the same. In Dalton theory, it's not quite right. It has there's a little thing that we're going to talk about later, which is isotopes. But anyhow, he's proposed that every atom, say, of oxygen was the same. It will have the same properties. And when they form compounds, they will combine in fixed proportions, as we saw in the example below. And that chemical reactions will produce rearrangements of atoms. Now, here we have, this is what Dalton uh, did not mention or took into account. So later on, it was discovered that not all the atoms of the same element have exactly the same, are exactly the same. For example, we have here the isotopes of carbon. Carbon exists in three different isotopes that have different mass. The atomic number of carbon is always 6, but uh, the isotope carbon 12 will have in the nucleus 6 protons, 6 neutrons, and the mass up to 12. Carbon 13 will have one more unit of mass. Carbon 14, another more, so 14. So, and they have properties that are actually unique. Carbon 12 is the more abundant in nature, but carbon 13 is very useful in something that we a technique that's called nuclear magnetic resonance. And carbon 14 is used to determine the age of objects because of its radioactive decay. So when you study fossils and things like that, and the application that I said about carbon 13 and nuclear magnetic resonance was applied to medicine because now we do um, image with for to help in the diagnosis. So anyhow, not all the atoms are the same. According to Dalton's, all of the atoms were at the smallest particle of, that will have the property of the elements, and that they were all alike. Uh, for now, we're gonna work with that. It's not relevant until we see the radiochemistry later. But for now, all of them are very much alike. And so now we have another number, a number that is very important in chemistry, and that number is the mole, or Avogadro's number. Now, this is the Avogadro's number is a really big number, but it represents the number of atoms that would be in 12.011 grams of carbon 12. And that number is 6.022 times to 10 to the power of 23 atoms. So that many atoms, that's a huge number. But this is just a number. Think about that. If you talk about a dozen eggs, you know that there's 12 eggs. If you talk about a gallon, that's another unit, and a gallon is 3.75 liters. So a mole is simply that number, that big number, 6.022 times 10 to the 23rd power. That's just a big number. Now, but we can use that number to calculate things that are very useful in chemistry, to calculate amount of substance. Now, with that, we know that 1 mole of carbon is 12.011 gram. Now, we have here, you have the symbols for atoms. So the mass of 1 mole of any given element or a substance is known as molar mass. What we have for water, we can calculate the molar mass if we have the formula by adding the mass of the individual atoms. So here I have the symbol of hydrogen. Atomic number is 1, and here is the mass. Let's do approx 1 gram. What is per mole? This is per mole. And oxygen atomic number 8, mass of a mole of oxygen, roughly 16, if you can see that here. So if you have that the molecular formula of water is H2O, we add the mass of 2 of the H's, so that will be 2 plus 16, that's 18 grams per mole of water. So we can use the sum of atomic masses to obtain the molar mass of a compound. Okay, and so in the law of definite proportions, we can use those masses. Uh, here, 1 gram of carbon dioxide, if you can calculate the molar mass. Carbon dioxide, see the formula is 1 carbon into oxygens. So carbon mass, atomic mass is 12, and then if we have 2 oxygens, that is 16, the mass as we approximated in the previous problem. And if you add that up, the mass, the molar mass of carbon dioxide is 44. And that gives you this composition. So about 73% oxygen and 27 carbon. And that is always the same. So we can use the mass of the atoms and we will find the exact numbers that we find in those experiments that were done previously to demonstrate Proust's law of definite proportion. Because if you see here 1 gram of carbon will have this amount of grams of oxygen and carbon. If you have 16 grams, then in the same proportion you will have 72.7% oxygen, which is 11.64. And now carbon monoxide has a different formula. The molar mass will be 12, the mass of carbon 16, the mass of oxygen that's 28, and is a different proportion as we can see, but it's definite. You always have the same relative amount, and it's different to that of the carbon dioxide. Now we can use this number, Avogadro's number, to calculate moles. We know that 12 gram roughly of carbon is 1 mole, contains 1 mole of atoms. So we can use the mass, for example, of something, grams, and convert that to moles by dividing by Avogadro's numbers. We can convert moles to particles by multiplying by Avogadro's number, and the other way around, we can use the number of particles divided by Avogadro's number, and you will get the moles. Later on, we're going to use this concept with liters. So we have unit conversion problems that we can do with this Avogadro's number. Think about that. Same we do, we say the dozen eggs. If I tell you to calculate how many eggs you have in a dozen and a half um, of eggs, you know that a dozen will be 12, and then another half is 6, so you will have 18 eggs. So we're going to be doing exactly that, but with moles. Okay, we have been talking about elements. So, and elements, so we talk about hydrogen and oxygen and others more. So there is a great say, accomplishment about organizing the elements according to its properties was done by Russian chemist uh, Dmitry Mendeleev. So, and he arranged initially the wasn't as systematic, just according to atomic mass, and discovered that there were gaps there and even predicted what elements would be discovered. And they were in many cases. They were found to be very accurate. This is the picture of what it looked like back the first periodic table. So notice to the left, the number 1, 2, 3, and so forth, um, in groups. He even organized that in groups. He used lithium, sodium, potassium, but that periodic table is not what we have right now. This is our modern periodic table. And we're going to be using that a lot in this course. The periodic table of the elements is organized in groups, which are these columns. And we're going to talk about those later. Alkaline metal, alkaline earth, noble gases, halides, and then we have periods, which are the horizontal lines, right? Going across, and a lot of metals. So this is the periodic table, and you're going to be using that. The small number above here is the atomic number. The number below is the mass, and it also has the name. But it was Mendeleev, the first one that did that. Here's looking up close at one of those little squares that we saw before. Here is the chemical symbol. This is iron, Fe. And well, this came from, obviously not, is not in English. The name is iron ferrum. So the atomic number is that small number. The mass of the average isotopes is weighted average. That's why it says so. Uh, and this is what you have in the periodic table. But here you have other properties. And the table below refers to Mendeleev predictions for germanium and what it was absorbed later. So notice that he predicted atomic mass 72 and the absorbed was 72.6. This is the weight average. Density, pretty accurate if you think about that. So Mendeleev was it was an enormous contribution. Nowadays we always use it. So now atoms are very real. They are the smallest, say, particle that actually has properties of that particular element. Is not the smallest particle. The atom can be subdivided, but we're going to study subatomic particles later. But it can even be nowadays seen in computer enhanced images. Now, let's talk a little bit about green chemistry. In the first chapter, we said that when we do green chemistry, we want to avoid having uh, dangerous reagents to produce a lot of waste and things like that. And there is a concept called atom economy. So we want to do chemical reactions in such a way that when we have two reactants, say that we have a reaction that is A plus B to give C. We want all the atoms as possible to be combined in no residue, no leftover, or things that can cause contamination. So that is the goal of green chemistry, replacing dangerous substances, hazardous substances, and using more abundant things than other, but also produce less waste. And that's the principle of atom economy. And so in green chemistry technology, one thing, remember that technology is something that is more applied to solve real problems. One example of green chemistry technology is when you replace the mercury fluorescent light bulbs with mercury-free light bulbs because mercury is a contaminant in a hazardous compound. So in other chapters, we're going to keep talking about the atoms and subatomic particles and more exciting things in chemistry.